Any space mission exploring the high-energy universe must be prepared to react rapidly to a sudden and sometimes rare celestial event. Astronomers at ESA are prepared to seize an opportunity not to be missed and race against time to capture the light before it fades. An alert is received by the teams at ESA. They first check to make sure the spacecraft can safely be reoriented towards the new source. If the decision is made to make this special observation, the team must quickly start the process of reshuffling the planned program of observations. This series of new commands is then sent to ESOC in Germany for transmission to the Space Observatory. Vast amounts of information about the hidden, high-energy universe lie within the precious data available from ESA. So what secrets does this data hold? And have profound new discoveries been made? With eyes that peer into the most energetic phenomena in the cosmos, ESA's XMM-Newton and integral space observatories have been setting records, discovering the unexpected, and helping to further our understanding of the unknown universe.
Invisible light, the star-forming region of the Orion Nebula, is a beautiful cloud of gas and dust. When XMM-Newton looked into this cloud, it discovered a huge area of extremely hot plasma revealed in X-rays.
This was quite a surprise, this detection in the Orion Nebula, which was not expected. The Orion Nebula is a nearby region where young stars are created. And if you look to the infrared, you see basically a very big hole in the center, and it was simply thought that this is an empty space. Now we looked with XMM and find exactly a hot gas filling out all this hole in the center of the nebula. The surprising point is that this hole was filled basically from one single hot star, which emits an enormous wind and plasma wind and fills this whole cavity in this nebula.
A supernova, marking the death of a massive star, can be bright enough to briefly outshine an entire galaxy. These explosions eject the outer layers of the star into the surrounding space, causing powerful shock waves.
And with this supernova remnant, the people were able to determine the velocity of the shock front. And if you have the velocity and the distance, you can calculate back when the supernova explodes. And therefore we could prove that this supernova explodes about 186 after Jesus Christ, and there were records from China and most probably also in Roman books, records about this supernova, and therefore it's the oldest recorded supernova, and we could now with XMM-Newton locate this supernova on the sky, which is not straightforward because at this time people were not using a coordinate system on the sky.
XMM-Newton made the first detection of two bright iron lines in the X-ray spectrum from a supermassive black hole lurking at the center of a distant active galaxy. X-rays are produced as matter is drawn onto the disk surrounding the black hole and from reflection by the disk material. By studying the varying brightness of the iron lines and that of the direct X-ray emission, astronomers observed a lag time between the variations.
But it confirms basically this interpretation, because from the basic physics we expect the second line a factor about 20 weaker than the primary line which we saw before. Now we have both lines and get a unique view so completely near to a black hole.
Using data from Integral, astronomers have identified a particular radioactive isotope of aluminium that is produced in massive stars and released into space by stellar winds or supernovae.
It is very interesting to astronomers studying massive stars and supernovae, because it gives a completely independent measure of how many of these supernovae exist, and allowed to determine that about every 50 years we should have a supernova in the galaxy, although we haven't seen anyone in several hundred years now by our optical telescopes.
Integral's wide field of view can be used to study the entire region at the center of our galaxy at one time. This region, known as the galactic bulge, is rich in bright variable X-ray and gamma-ray sources.
There, we have every time that we can observe this during the year, we have a program to go back there every 3 days, once per orbit, and take a sort of snapshot, several hours of observations, and see what is happening there. And the fascinating thing is it changes all the time. That's the thing about high-energy astronomy. You don't see the same sources all the time. You see sources appear, disappear. We even had one moment when all the known sources were off, and you started suddenly to pick up some very faint ones, which you had missed before. And otherwise, we see transients coming up. And this kind of information is then distributed from here and from our colleagues at the Integral Science Data Center to the world. And other observatories then often enough turn to these sources, follow up what they are doing, and add the information that we get from our monitoring.
Supermassive black holes have been seen by Integral lurking in many galaxies. When galaxies closer to our own were searched, surprisingly few black holes were found.
We would expect from other astronomical clues to see a certain number of such black holes, and the expectation was that, well, they may be a little bit enshrouded in gas, and so at lower energies, like with XMM, you would have maybe missed them, but once we turn integral on them, which peers through the gas and cloud, we would see them. But now the evidence is becoming more and more clear that we are actually not seeing enough of them, which may either lead to that you need a completely different explanation for the high energy background that you have, or that people have to involve an evolution in time, that actually these things have changed over the evolution of the universe, and we're not seeing exactly the same sources now in more recent universe than we expect that we get from other information looking further back in time with other telescopes.
These really are just a small taster of the celestial wonders previously hidden to astronomers and revealed by these remarkable space observatories. XMM-Newton and Integral will continue to keep watch on the ever-changing high-energy X-ray and gamma-ray universe, react to sudden, violent outbursts, and help to solve mysteries of the cosmos. I'm Rebecca Barnes. Thank you for watching the Science ESA vodcast.